Welcome back. In the last session, we had seen one conclusion, like for all non-linear elements, we should define resistance in a dynamic way. We should not define in a static way. If you define in a static manner, that is giving wrong value. It is not representing its own resistance, means its internal resistance. It is representing the external load value. That is what we had seen with respect to ideal voltage source and ideal current source, right? And another conclusion with respect to linear elements like a resistor and n-type semiconductor, p-type semiconductor or intrinsic semiconductor, we can define the resistance either in a static way or dynamic way because the element is linear. If element is linear, we can define either way, right? Now, let me give you a generic relation, static definition and dynamic definition. Remember, it is not only for resistance. See, what is resistance mathematically? Voltage by current. Static voltage, static current, or a voltage V1 and then I1. That is what is resistance or static resistance. And delta V by delta I, that is nothing but dynamic resistance. If element is linear, just define V1 by I1 or V by I. If element is non-linear, we should define delta V by delta I. That is the reason why if you take PN junction diode and if you define the resistance of PN junction diode, by default the PN junction diode resistance is dynamic resistance. Even though I don't specify resistance of PN junction diode, it is under if it is under forward bias, forward resistance. If it is under reverse bias, reverse resistance. Why? Because PN junction diode is non-linear device. Therefore, the resistance by default is nothing but dynamic resistance. That's why we represent normally with small letter forward resistance when I say small RF. What is the meaning of small RF? Dynamic forward resistance. No need to attach the term dynamic. By default, that is dynamic resistance. We should not define static resistance for PN junction diode because PN junction diode is a non-linear element. I'll explain those points in detail later on, and it is related to resistance. But not only resistance, let me ask you, sometimes, this is generic, sometimes people define current I is equal to Q by T. Sometimes people define same current I, small I is equal to dQ by dt or delta Q by delta T, anything is fine. Now, sometimes people define capacitance C is equal to Q divided by V. Sometimes people define same capacitance C is equal to dQ by dV, right? Sometimes people define electric field E is equal to V divided by D or L, anything is fine. And sometimes people define electric field E is equal to, if I take only magnitude, dV by dx. Sometimes people define velocity V is equal to distance by time, and I can say distance instead of L, distance by time. And sometimes people define velocity is equal to dx by dt. See, if you observe clearly, I can categorize the definitions, right? Here, these are all static definitions. See, not only resistance, where we have static resistance and dynamic resistance. You take any parameter which is what is defined with two variables and the ratio of two variables, then we can define either static way or dynamic way. When to define static way, when to define dynamic way, that is what I am taking, and these are all useful. Now let me tell you, this is what is static definition, the static definition, and this is dynamic definition. This is what is dynamic definition, right? Now, when to define static way and when to define dynamic way? Very simple. In the case of resistance, right, the same category, or resistance R is equal to V divided by I, right? And then what is this? Small r is equal to dV by di, right? Therefore, if you see here, I told you, right, when to define the resistance in a static way, if the relation between voltage to current is linear, if the relation between voltage to current is linear, then you can go ahead either static way or dynamic way, right? If the relation between voltage to current is not linear, then we should not define resistance in a static way. We should go to dynamic definition, which is delta V by delta I. Similarly, let us go to the current part. This is already we have seen, right? Now I am applying the same technique to all remaining variables. Here, if you ask me what is current, current definition is nothing but the charge movement with respect to time, right? And here the current is nothing but rate of flow of charge, or the amount of charge which is what is moved, which is dq, in what time? Delta t time, or the change in time. Therefore, looks like both are same, but when to define this? Same as your resistance. If the relation between charge to time is linear, then you can define current is equal to Q by T. If the relation between charge to time, the change in the charge or the charge variation or charge movement with respect to time is not linear, then we should not define I is equal to dq by dt. Let me give you example, means how to get it. Let us say resistor, if you take a resistor, now I am not speaking about resistance, now I am speaking about current. When I speak about current, let us say resistor is nothing but what? Basically, it is a wire. When I say this is the wire having area of cross section, and this is what is having length L, right? Now this is what your element. This you can equally represent as a resistor, where R is equal to rho L by A, and this is what is having area of cross section, and this is having some conductivity. Therefore R is equal to 1 by sigma, that is nothing but rho, and L divided by A, right? Now if I ask you, when I apply the voltage, let us say I am applying the voltage. If I apply the voltage across the resistor, then that is nothing but I am applying the voltage here. Both are same, but here representing with a wire with the dimensions. Here wire in electrical domain, resistance. This is what is V plus minus, and there is a current I. Definitely there is a current I. Now I am not giving the relationship between, or I am not trying to get the relation between V and then I. That is already done. We have seen so many examples with respect to ideal voltage source, ideal current source, resistor, etc. Now what I want to explain the current with respect to charge and time. Therefore, if you see here, what is current here? Here, if I say I is equal to, capital I is equal to Q by T, or I can say I is equal to delta Q by delta T, or dQ by dt. Both are same if delta T tends to 0. Now, if I say this definition, what is the meaning of it? Current is nothing but charge movement with respect to time, right? First of all, why there is a charge movement? We have so many carriers or so many electrons. When there are so many free electrons at room temperature, let us say this is at room temperature and this is copper material, right? Because of what? Because of battery, there is electric field, right? There is electric field, and because of electric field, therefore what is that electric field? That is because of the voltage, and because of the electric field, there is a force, electrostatic force on the carriers which are there inside the material. If there is electrostatic force, then depending upon the direction of the force, the carriers will move in a particular direction. Or strictly speaking, this is plus, this is minus, right? Your electrons will be attracted by positive electrode, your electrons will be repelled by negative electrode. Therefore, because of the battery, it is repelling the electrons and attracting the electrons. Therefore, the direction of the force due to electric field will be like this. Mathematically, F is equal to E into Q, where Q is negative because electron. Therefore, the force will be, even though electric field is like this, the force will be opposite to the carrier because there is negative charge. This is also satisfied. Therefore, both are fine. If you are confused, don't go with that. Very simple. The battery, this is positive, this is negative. It is repelling the electrons, and this is what is attracting the electron. Therefore, electrons are moving like this. Therefore, we know that voltage is constant. When voltage is constant, electric field is constant. When electric field is constant, then the force on the body, therefore, when voltage is constant, right, then this is what is giving electric field, because E is equal to V by L, voltage by L. V is constant, length is constant. Therefore, this is also constant. Your electric field is also constant. If electric field is constant, right, this is what is giving what? This electric field, this is giving the force on the body, force of the charge carrier. F is equal to E into Q. Electric field is constant, therefore this is constant. Charge of the carrier is constant, therefore your force is also constant. when force is constant, then tell me, according to Newton's second law, right? When force is constant, then what we get? When force is constant, what we get? There is a charge movement because of which we get something called drift velocity, Vd. Maybe instead of that, I can directly from here, therefore this is what I can say in a different way. Then electric field is constant, then immediately the drift velocity Vd is equal to mu into E. When E is constant and the temperature is constant, therefore your Vd is constant. When velocity is constant, what do you mean by that? The electrons which are moving per unit time, right? The distance per unit time, distance per unit time, distance per unit time, constant. Therefore I can say the charge which is what is moving per unit time. Therefore that is what is constant. That's why your current is constant. Therefore I can say your current I is equal to constant. If I is constant, let me tell you, if I is constant, what does it mean? This is nothing but what? If you take Q to T, therefore what do you mean by Q to T? If I take the plot, this is nothing but time T, and this is what is charge Q. Then at time T is equal to 0, at time T is equal to 0, let us say switch is closed, at time T is equal to 0, let me take like a switch. At a time T is equal to 0, switch is closed. At time T is equal to 0, right, there is no charge, and when switch is closed, the charge is moving, right? How much charge is moving per unit time, that is what it is, right? Therefore, if you ask me, and this is what is my observation point, if I say this is what is my observation point, the moment when you close the switch, then the electrons are crossing. Therefore, how many electrons are crossing? Let us say 10 electrons in 1 second, 10 electrons, 1 second, 10 electrons, 1 more second, 10 electrons, 1 more second. But if you count the time, let us say this is 0 and this is 1 second and this is 2 seconds, just for your understanding, I am taking. Therefore, now tell me, when you close the switch, then charge movement is not there. The moment you close the switch, let us say 10 electrons are moving in 1 second. Therefore, in 1 second, 10 electrons are moving. Let us say 10 electron charge, whatever you have. Therefore, 10 electrons are moving. In the 2 seconds, because per second, 10 electrons, because velocity is constant. When velocity is constant, 10 electrons per second. Next second, 10 more electrons, but total number of charge particles which are moving per unit time. Therefore, from here to here, 10 more, therefore total 20 and 30. If you see, therefore here you will be having 20 electrons in 2 seconds and the total number of electrons which are crossing, because this is what is my observation point. How many electrons are crossing per unit time? The total charge which is what is crossing per unit time. If you see, that is what is having the relationship between the charge with respect to time is linear. If the charge with respect to time is linear, then we can define the relation between charge to time or the relation between dependent parameter to independent parameter, which is nothing but the ratio of these two is nothing but your current, that you can take like a static way. You can take it like a static way because the relationship between charge to time is linear. If the relation is linear, right, you can go for linear definition or static definition. Either you can define static way or dynamic way. I hope everybody understood. It is not only for resistance. If the relation between voltage to current is linear, then static way or dynamic way. Similarly, if the relation between dependent parameter to independent parameter is linear, then you can go for static way or dynamic way. I can explain mathematically also. What do you mean by, let us say this is y-axis and this is x-axis. If I say this is what is your y-axis and this is what is your x-axis, then tell me what do you mean by q by t? Q by t is nothing but what? Y by x. Therefore, what is that q by t? Or if you speak with respect to generic way, y by x. What is y by x? Slope. Therefore, this is nothing but slope. Slope of the curve. If you take a linear curve, what is the slope? Slope is constant, right? Therefore, that is what is your current. Therefore, the slope of the curve or the slope between dependent parameter to independent parameter is nothing but the definition or the ratio. If that is linear, then you will have constant slope. That is what is our current. If that is not linear, then slope is not constant. Slope will vary. If that is kind of non-linear, let us say if the relation between q to t is non-linear, let us say this is what your q, then if this is what is going like this, let us say exponentially. If that is what is going like this, right? I'll give you example where you see the relation between charge to time is like this. Maybe if you take a resistor, or conducting element where with fixed voltage, fixed electric field, fixed force, fixed drift velocity, current is constant, means the charge to time is linear, then I can define the current as I is equal to Q by T in this element for linear element. Now coming back to, let us say the relation between Q to T is non-linear, then basically we cannot go for Q by T, because if you go for Q by T, what do you mean by Q by T? Let us say this is what is time T1 and this is what is time Q1. If you define Q1 by T1, then that is nothing but what? Slope of the curve, which is what is passing through the origin. What is that? If I say this is what is the point and this is what is the point, if you join these two, whatever slope you get for this line, that is nothing but Q1 by T1. But strictly speaking, that is not a straight line, that is a non-linear curve where we cannot define static way like Q1 by T1. We have to define like wherever you are operating, let us say this is what is time T2 and this is what is charge Q2, then delta Q whatever you have and then delta T whatever you have. We have to define delta Q by delta T, then you'll get slope of the curve exactly at what point you are operating you're trying to operate or you're trying to find the incremental changes like delta Q by delta T. That is what. Therefore, the slope is different. Here 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 the slope is different for non-linear curve. Therefore, the slope of non-linear curve is depending on the operating point. I'm going to extrapolate or I'm going to use this point later on when I explain DC analysis or AC analysis of BJT amplifiers, which I already explained little bit in the introduction class, which is nothing but BJT DC analysis and BJT AC analysis, right? Here, the incremental changes, delta Q by delta T, delta V naught by delta Vi, output voltage change divided by input voltage change, voltage gain. The voltage gain of your amplifier is depending on, which is nothing but, the slope of the curve is nothing but the gain, that is what is depending on operating point. Means the slope of the non-linear curve is depending on operating point, because basically your BJT amplifier, MOSFET amplifier, these are all non-linear amplifiers. Therefore, the gain of the amplifier will be depending on operating point. If operating point changes, definitely gain changes. Similarly, if at a different point you will have different slopes, therefore because of non-linearity. You may ask, those things we see later on when I speak about non-linear system or non-linear amplifier, how to make it linear, those things I speak later on. For the time being, I'm just trying to explain when to take static definition, when to take dynamic definition. Very simple. If the relation between not only current or not only resistance, you take capacitance, you take electric field, you take velocity, wherever you have ratio of two variables, when to take in a dynamic way and when to take in a static way. If the relation between dependent parameter to independent parameter is linear, then go ahead with static definition or dynamic definition. Both are true. If the relation between dependent parameter to independent parameter is not linear, something like this, the charge which is what is changing with respect to time is not linear, then we should not take static definition. If you take static definition, you'll get wrong answer. It is like slope of a line which is what is passing through origin. If you take Q1 by T1, which is not correct. That is what I want to say. Therefore, if the system or the element is non-linear and you have two variables, then you can go ahead with dynamic definition. I hope everyone understood. Maybe I can give you a small example where you have charge to time is non-linear. That is very simple. In this case, resistor I have taken, you take capacitor. If you take capacitor, therefore if you take capacitor, right, then let us say this is what is the switch, and then I have some resistor. Then if this is what is the scenario, we have some battery, and then R, it has some capacitance. Then tell me, if you close the switch at a time t is equal to 0, then definitely your capacitor charges exponentially. Then the charge which is what is stored by your capacitor also stores in exponential way. Then if you take the charge to time, this is what is charge to time, it charges exponentially. Initially it is trying to charge faster, then as time progresses, because of the opposition by your capacitor to the battery, then what will happen? The charge injection or the charge storage will be decreasing with respect to time at higher times. Therefore, you see the relation between charge to time is non-linear. Okay, but I'll explain a little bit about capacitor later on, because if you understand capacitor action very well, I can say 50% of MOSFET operation is over, because basically MOSFET is nothing but a capacitor between gate and bulk, and we see capacitance action. But there, in the case of MOSFET, metal oxide semiconductor, there are two plates. but one is metal and another is semiconductor. But if you take parallel plate capacitor, both are conducting plates. Okay. If time permits, we will explain, or I'll explain the capacitor operation and try to correlate to MOSFET action also. Okay, fine. I hope everyone understood. Now, you just take the static definition and dynamic definition. Maybe you can take the current definition, current Q by T, and then Q by T linear and then non-linear. Here, this is what is linear. Then here, this is what is non-linear. If this is what is non-linear, we should take small I is equal to dq by dt. This is what is current definition. And if this is linear, then you can take either I is equal to q by t, or you can take dq by dt. Both are true. Both are true. But here if you take I is equal to q by t, this is wrong because this is non-linear. Okay. You take this, then I'll dictate one point. With that, I can say part of the fundamentals is over. Okay, take it. Therefore, the conclusion with respect to analog circuits where we use all semiconductor devices with PN junction, right? PN junction diode, BJT, MOSFET, right? You take all these three elements are non-linear, therefore the definition of resistance is by default dynamic resistance. Okay. When I speak about input impedance of an amplifier, because input impedance of BJT amplifier, input impedance of indirectly the BJT device, which is what is present, we should take it like dynamic definition, not static definition. If you take static definition, that is wrong because the element is non-linear. That is what I want to say. Okay, now let me explain little bit about PN junction diode, BJT and MOSFET, then we can go to the BJT amplifiers part. Okay. Now, let me explain number one, PN junction diode. What is the symbol of PN junction diode? Let me take the cross-sectional view of PN junction diode. If you take PN junction diode, this is P-type material, N-type material. I am not going into the details, I am just starting with some fundamentals. Then if you don't connect any voltage, we have depletion region. I am just taking few impurity atoms. This is what your depletion region, let us say. Then we have electrons. We have holes here because P-type material is having majority carriers or holes. And what are the minority carriers of P-type semiconductor? They are nothing but electrons. They are very few in number. And here minority carriers are holes. They are very few in number, and already there is a depletion region. And why depletion region and all, I am not going into the two details. Now what I want to say here, because there is a space charge region, then we have something called contact potential, which is nothing but open circuit voltage, which is what is V0, that I am not deriving. If you ask me what is that V naught is equal to Vt ln Na Nd divided by Na square. What is Na? The accepted doping concentration of your p-type semiconductor, and Nd donor impurity concentration of your n-type semiconductor. For a typical doping concentration, for a typical p-n junction diode, right? What is a typical p-n junction diode? We will have typical doping concentration. What is typical doping concentration? I'll come to that part. Therefore, for a typical p-n junction diode at a room temperature, let us say at room temperature, temperature is equal to, let us say 300 Kelvin, right? If you ask me what is V naught, that V naught is equal to 0.7. That V naught is nothing but 0.7. What does it mean? Means that's why people say the cut-in voltage of p-n junction diode is nothing but 0.7. Remember, when you apply the voltage, let us say forward voltage, when you apply the forward voltage, then the barrier whatever you have, or the depletion region whatever you will have, that is what is acting as a barrier for your forward bias voltage what you are applying externally. What I want to say, let us say this is what your p-n junction diode. Now, when I say this is what your p-n junction diode, this is P, this is N, and whatever barrier we have, this is what is your depletion region due to diffusion of majority carriers from N to Pn and P to N. Then we have electrons here. These are all majority carriers. Let me ignore for the time being minority carriers, because under forward bias we will not see, or we can ignore the current due to minority carriers. Only majority carriers will participate into the conduction. What are maybe, and this is what your depletion region. Now when I apply forward bias voltage, P is connected to positive and N is connected to negative, right? This is what is plus and then this is what is minus. Now as I told you, whether this is p-n junction diode or a wire or a capacitor or inductor or BJT 2 terminals, MOSFET 2 terminals, doesn't matter for the battery. The job of the battery is always try to push the electrons and then pull the electrons. But in between these two terminals of the battery, we connected p-n junction diode. When you connect p-n junction diode, tell me, this is what is trying to push the electrons, this is what is trying to pull the electrons, right? But inside the p-n junction diode, we have two types of carriers. Number one, electrons, number two, holes. But remember, let me tell you a point. Here, when I say electron, that is nothing but a free electron, the electrons which are there in the conduction band. And when I speak about holes, the electrons which are not there in valence band. Here, when I speak about electron movement in the n-type semiconductor, that is nothing but electron movement in the conduction band. When I speak about hole movement, that is nothing but valence electron movement. Physically, there is nothing called hole. Hole is nothing but absence of an electron in the valence band. Therefore, electron can come and occupy that vacant state which is there in the valence band, and it can move from one vacant state to another vacant state. That is nothing but valence electron movement, which is nothing but hole movement. There is nothing called hole, but it created a vacant state. Then the free electron can become a valence electron, but it can move through vacant states. That is nothing but valence electron movement. In the n-type, the electron movement is nothing but free electron movement or conduction electron movement, and the whole movement is nothing but valence electron movement. Whatever it may be, it is ultimately electron movement only. But whether it is conduction band electron movement or valence band electron movement, that is what it is saying, electron movement, hole movement. I am not going to those details, that is fine. Now, if you see here, when I say this is what is minus, this is what is trying to push the electron. When the electrons are trying to move, but I told already we have a negative charge here, positive charge. The negative charge, whatever we have here, it is opposing, because negative charge and an electron, negative charge repels. Therefore, the negative charge and the electron whatever we have, both will be repelled. Therefore, the depletion region is acting as a barrier for the majority carriers. Similarly, the hole is treated as a positive particle, virtual positive particle. It's not a physical particle but virtual positive particle. Then the positive charge whatever you have here, the positive charge and then the positive charge will be repelled. Therefore, the hole cannot cross the depletion region. Now, the battery is the one, when you are connecting into forward bias, the battery is the one, that is what is giving the energy to the carriers which are there in the n-type, and to cross the barrier after overcoming the depletion region. But what is the depletion region voltage which we already derived or which we got, which is nothing but V naught, that is nothing but contact potential. For a typical doping concentration at room temperature, that V naught is nothing but 0.7, means I need to apply externally such that the electrons will overcome the barrier. Therefore, what is the minimum voltage we need to apply such that the battery can overcome the barrier whatever you have inside the PN junction diode. Therefore, the majority carriers from N, they will cross from N to P and they'll move through holes because these are all breaker states and they're coming out of PN junction diode and then reach the other terminal of the battery and forming the loop current. That is what is defining your current, which is forward bias current. I hope everybody understood. Right? Therefore, whatever barrier you have, which is nothing but plus minus V naught, that should be overcome the battery. Therefore, this is what your forward bias voltage. Therefore, what should be that voltage? That should be greater than or equal to V naught. It should overcome the barrier what you have. That is what people say. The minimum voltage to be applied such that you see significant current through the PN junction diode after overcoming the barrier is nothing but the cut-in voltage V gamma. That is nothing but 0.7 because the barrier voltage is 0.7. What I want to say is V naught is 0.7, V gamma is 0.7. Whatever barrier voltage you have internally, that much voltage we need to apply to overcome that. Then you see the current, which is what is loop current, and that is what your PN junction diode current. Here the point is why I am explaining all these things. The point is the V naught or indirectly the V gamma is what? V naught is equal to Vt ln Na into Nd divided by Ni square, right? Vt is nothing but volt equivalent of temperature. Therefore, where Vt is equal to Kt by Q, which is basically 26 millivolt at room temperature. And what is Ni? Ni is nothing but intrinsic carrier concentration. Intrinsic carrier concentration. It is also function of temperature, but if you ask me at room temperature what is this value, 1.5 into, or I can say the formula is A naught T cube exponential of minus Eg naught, energy gap, into Kt. A naught is a constant, T is the temperature, energy gap of the material, let us say silicon semiconductor, then Eg naught is equal to 1.21 electron volt, because Eg naught means energy gap of semiconductor at 0 Kelvin, therefore which is 1.21 electron volt, and then K into T at room temperature, this value is 1.5 into 10 to the power of 10 per centimeter cube. This is at 300 Kelvin. Therefore, if you substitute all these things, Vt 26 millivolt and Ni square, this value 1.5 into 10 power 10 whole square, which is 2.25 into 10 to the power 20, then Na into Nd. What is Na Nd? That's what? That depends on doping. Therefore, what I want to say, for a typical doping where Na and then Nd, if you ask me, Na comma Nd, if they are in the order of 10 to the power of 14, in the order of 10 to the power of 14 per centimeter cube, I'll come to this point, 10 to the power of 14 per centimeter cube or 10 to the power of 13 per centimeter cube, right? In that order, then your V naught will be, then V naught will be in the order of 0.7 at room temperature. What I want to say, your V naught is function of doping concentration. If you increase the doping concentration, your V naught will change. Your V naught will change, but it is about 0.7. Therefore, it will be 0.7, 0.71, 0.72, 0.73, 0.74. But remember, don't say 0.7 will become 2. No, because even though Na and D both are changing significantly, but because this is log of something, and that something is very high, but the log of something will be very small. Maybe I can give a small example. If you take, what is that example? If you take log 10, what is log 10? 1. But what is log 1000? Log 1000 is nothing but what? 3. Therefore, even though 10 is becoming 1000, which is very significant change, but the absolute value of log is not that much significant. Therefore, even though your doping concentration is varying significantly, but log of very significant value is very small change in V naught. Therefore, but typically it is 0.7, but if doping concentration is different, it could be like in the range like 0.6 to 0.8 or 0.55 to 0.8 to 0.85. Therefore, that is what is your V gamma, that depends on doping concentration and room temperature. At room temperature, if the doping concentration is typical doping concentration, which is in the order of 10 to the power 14 impurity atoms per unit volume, then you will get V naught in the order of 0.7. Therefore, your V naught, the observation or the conclusion is, your V naught is function of temperature and the doping concentration. At room temperature and the typical doping concentration, your V naught is equal to 0.7. Why I am explaining this? If you take BJT, we have two PN junctions, emitter PN junction and collector PN junction. Then both PN junctions will have different doping concentrations. That's why both will have different cut-in voltages. This is the point which I need to explain the conditions for saturation region, conditions for active region, or conditions for cutoff state. That is the reason why I am explaining what is V naught and then why it changes. But don't think that always PN junction diode will have a cut-in voltage 0.7. But typically, because we are dealing with the typical PN junction diodes in the lab, always we take V gamma is equal to 0.7. But remember, that is not always 0.7. Everybody understood? That's fine. Now, let me explain little bit about this 10 to the power 14 per centimeter cube and then 1.5 into 10 to the power 10. Then I'll go to the VI characteristics of your PN junction diode and diode approximations. Then later on I can go to BJT also. Okay, take it. Small correction, this is Ni square is equal to this value, therefore this is Ni square, but this is Ni value. Therefore Ni is nothing but intrinsic carrier concentration, but this is nothing but Ni square. Okay, now let me explain a little bit about this, like what is 1.5 into 10 to the power of 10 per centimeter cube and what is this 10 to the power of 14 per centimeter cube, which is like typical doping and at room temperature. Let me erase. Now if you take pure silicon, right, because what is silicon atomic number? Silicon atomic number is 14. Then what is electronic configuration? 1s2, 2s2, 2p6, 3s2, 3p2, where it has valency is equal to 4, the number of electrons which are present in the outermost shell, therefore is equal to 4, therefore valency is equal to 4. Then it is sharing, it is participating into the covalent bonding. To get stability, it is sharing with 4 silicon atoms, therefore it is getting stability. That is what people say, the structure will be, the silicon is having the bonding with respect to 4 silicon atoms. This will be continued, but let me take, this is what is my interested, therefore it has already 4, 1, 2, 3, 4 and sharing with 4 and then everybody is giving something like that, therefore this is what is getting stability, right? Now if this is what is the case, let us say this is what is the silicon material, but if you ask me how many silicon atoms are there, if you take 1 cubic centimeter silicon material, what does it mean? 1 centimeter width, 1 centimeter breadth and then 1 centimeter height, right? How many silicon atoms are there? These are all real values, which is another 5 into 10 to the power of 22 silicon atoms are there. Silicon atoms are present per centimeter cube. Means these many silicon atoms are there per centimeter cube. What does it mean? What is this? Can I write it like 550 into 10 to the power of 7 into 10 to the power of 7 into 10 to the power of 7? 3 7s are 21 and then 10, 22. Therefore these many atoms are there per centimeter cube. Means what is this value? 50 crores silicon atoms are there per centimeter cube. It is not 1 crore, it is not 2 crores, it is not 1 lakh crore, it is not even 1 crore. It is 50 crores. Those many silicon atoms are there per centimeter cube. What is per centimeter cube? I can say half of the size of the cap. Therefore, if you take that much silicon material, we have 5 into 10 to the power of 22 silicon atoms are there per centimeter cube, and then each silicon atom is having covalent bond with respect to 4 adjacent silicon atoms. Therefore, it got stability. Therefore, now tell me, if all silicon atoms are in the bonding, right, then there is no free electron. There is no free electron. If there is no free electron, and if you take this material, right, then if you connect 2 terminals and then if you give battery, you will not see any current. But remember, if I say at a temperature is equal to 0 Kelvin, which is minus 273 degrees Celsius, which is not 0 degrees, it's not minus 10 degrees, it is minus 273 degrees Celsius. That is what is 0 Kelvin according to Boltzmann. At this temperature, we don't have any energy which is coming from external temperature. Let us say, then whatever silicon material we have, let us say 1 centimeter cube of silicon, then if you take 2 terminals, then when you apply battery, right, this is what is plus V, then whatever current you have, current is absolutely 0. There is no current because all silicon atoms are in the covalent bond. If all silicon atoms are in the covalent bond and are sharing with 4 silicon atoms, then all valence electrons are in the bonding, then there is no free electron. Remember, we get current due to free electrons, not due to valence electrons. Therefore, there is no free electron. If there is no free electron, then obviously there is no current. But remember, at a temperature is equal to 300 Kelvin. I am just taking one example, which is room temperature. I can say this is 27 degrees Celsius. Now, you know, some covalent bonds will be broken. Why some covalent bonds will be broken? At room temperature, according to Boltzmann, energy of the particle due to heat or due to temperature, right, is nothing but K into T, then T is equal to 300 Kelvin. If you calculate, you will get 26 milli electron volt. Then those many photons, if those are all captured, if some of the photons are captured by some of the silicon material or silicon atoms, then some of the bonds will be broken. Now if you ask me, what is that bond breaking ratio? That is what people call it as, let us say, once the bond is broken means, let us say this bond is broken, now the electron whatever you have, that is what is becoming free electron, and absence of an electron is nothing but a hole, and this is what is called, this is electron, free electron, and this is what is hole, and this is what is called electron hole pair production. This is what is called electron hole pair production. Therefore, what is that electron hole pair production ratio? If you ask me, that ratio is nothing but EHP, electron hole pair production ratio, is 10 to the power of, if you ask me, 10 to the power of 12:1. It will be in the order of 10 to the power of 12:1. What does it mean? For every 10 to the power of 12 silicon atoms, one bond will be broken. For every 10 to the power of 12 silicon atoms, for every 10 to the power of 12 silicon atoms, one bond is broken. One bond is broken. If one bond is broken, then you will get, for every 10 to the power 12, if you take 10 to the power 12, what is 10 to the power 12? 10 to the power of 3 into 10 to the power of 7, means for every 1000 crores of silicon atoms, one bond is broken. Then one free electron, one hole. Therefore, this is electron hole pair. Similarly, for every group of 1000 crores of silicon atoms, one electron, one hole. For every 1000 group of 1000 crores of silicon atoms, 1 electron, 1 hole. If you take a complete silicon material having 1 centimeter cubic structure, then where 5 into 10 power 22 silicon atoms are there per centimeter cube, then tell me for every 10 to the power of 12 silicon atoms, if one bond is broken, if one electron hole pair, then tell me in the order of 10 power 22, right? For every 10 to the power of 22 silicon atoms, how many bonds are broken? If you calculate, you will get that x in the order of 10 to the power of 10, and the real value, that is what people call it as the real value is, that is nothing but n is equal to P. What is n is equal to P? Number of electrons per unit volume per centimeter cube, or number of holes per unit per centimeter cube. We know that if bond is broken, one free electron, definitely one vacant state, which is nothing but a hole. How many electrons are there? How many free electrons are there? Those many vacant states are there. Those vacant states people call it as people call them as holes. Therefore, n is nothing but electron concentration, P is nothing but hole concentration. That is what people call intrinsic carrier concentration, because this is pure semiconductor, which is intrinsic semiconductor. That is what is 1.5 into 10 to the power of 10 per centimeter cube. That is what I gave. That is what I gave before, right? The intrinsic carrier concentration Ni is equal to 1.5 into 10 to the power of 10 per centimeter cube at room temperature. At room temperature. This is what is intrinsic carrier concentration. Okay. Let us continue in the next session. Then I'll explain the meaning of typical doping, and with that I can say, and I'll give you the current to voltage relationship of a PN junction diode. Then let's plot the VI characteristics of PN junction diode. Then let's see the approximations. Okay. Thank you.